Anybody can reply?
Yes, sir.
We have started. So, what is entropy? I want some revision from your side now. Okay, what is entropy? Anybody? Entropy is what? Okay, what is entropy? Anybody? What is entropy? Anybody can reply?
Sir, entropy is a measure of molecular disorder.
Yeah, correct. Your name?
Kunal Chite.
Huh?
Kunal
Kunal,
sir.
Kunal, okay, correct, good, good. Current is also giving disorder in the system. So entropy is a disorder in the system, or degree of measure of degree of disorder in the system, or it is, we can say it as a molecular randomness. So generally we are calculating the entropy by using which formula? ds is equal to dq by t, or integration dq by t for reversible process. And for this we have taken a base that Clausius equality or inequality theorem, that is cyclic integral of dq by t is equal to 0. Therefore, for a reversible process, this integration dq by t or del q by t is representing a property, and here this del q by t is coming as a property. Okay, so this del q by t is coming as a property. The entropy change can be obtained by taking integration, so it is a mirror image, consider it as a, so therefore delta s is equal to, we can say, is equal to, here we can say delta s is equal to, here we can write delta s is equal to, here q divided by, if integration limit is too much nearer, okay, fine, limits are integration are very close to each other, there delta s directly we can take it as a q upon tu. Okay, and if the limits are too much, okay, difference is more in the limits, then we can say ds delta s is equal to, we can say here s2 minus s1, delta s equal to s2 minus s1, and is given by equation, what we can say, equation is equal to, here integration from 1 to 2, if the system is changing the state from 1 to 2, integration dq by t. So with the help of this equation one can calculate henceforth the entropy change during any thermodynamic process. So entropy change, whatever definition we have taken, it is only applicable for reversible process. But afterwards, all the processes are irreversible. For them also, we are calculating the entropy change equal to reversible process, and we are assuming that minimum entropy change, it should be equal to reversible process. And then entropy, afterwards we have learned that it is a second law of thermodynamics, it is outcome. Then entropy transfer is associated with heat transfer. If heat transfer, if heat to work transfer is taking place, then entropy transfer is take place. If work to work transfer is taking place, there is no entropy transfer, because work is pure form of energy. In the pure form of energy, disorder is not there, and therefore no entropy transfer will be there when work to work transfer will take place. But when work to heat is there, again pure form to low grade form, again there is no entropy transfer, because but low grade to here pure grade, higher grade, then entropy transfer will take place. Here also work to heat, again pure to low, again there is no entropy transfer will take place. Then again we have discussed about the important points, remarkable points about the entropy, that is entropy change uh, will have the same sign of the heat transfer. So if the heat is added, entropy will increase. Okay, again, and here also we have to remember that entropy is a non-conserved property. It is not conserved. There is increase in entropy, but entropy is not conserved like our energy. Therefore, there is no such thing or principle like conservation of entropy. There is principle is conservation of enthalpy is there, but conservation of entropy principle is not there. Conservation of entropy, that kind of principle is not there. But the total entropy of the universe is always increasing. It is not that total entropy of the universe is remaining constant. So total entropy of the universe is always goes on increasing, because irreversible processes here, the entropy of the irreversible processes always goes on increasing. Only if the process is reversible, then and then only entropy transfer will be equal to zero. Only for reversible process, ds is equal to, we can say it as a zero. What is only this process for only reversible processes. Otherwise, here for any irreversible processes, here entropy change is equal to, where it is more than zero, okay, greater than 0. Therefore, always entropy is goes on increasing in case of the irreversible processes, and all the processes in the universe are irreversible. Therefore, entropy change in of the universe is always goes on increasing. Okay, then heat transfer increases the entropy because it is a positive sign conventions. Okay, so here it is heat transfer to a system increases entropy, because heat added means entropy goes on increasing. If it is removed, if the process is cooled, then we can say entropy is goes on decreasing. Then in fact possibilities of heat transfer is out of the system may be irreversible. Then here, for any process, I have told you that for any process, if you want to calculate the entropy change, we have to go for this integration 1 to 2 here, dq by t. So if you calculate dq by t there, that is nothing but the entropy change for any thermodynamic process. Now also we have gone for, this is very important derivation, many times they are asking, that is here entropy change during thermodynamic process. And here for that we are assuming that some books they have considered mass of the gas as a 1 kg, or some books they are considering it as a m kg. If it 1 kg is there, m will become for specific mass, we can say it as a, for if the mass is one specific mass, specific entropy we can calculate. Specific entropy we can say here mass m is equal to specific entropy. This is entropy, total entropy. Specific entropy means for 1 kg of gas, m is equal to 1. So in that case, m is equal to 1 for here specific entropy. Then let m kg of gas having pressure P1, volume V1, and absolute temperature T1, and entropy S1 be heated by thermodynamic process. That means we have this ideal gas, it has changed its phase state from pressure, volume, temperature, that is P2, V2, and T2, and entropy will be S2. Then what is S2 minus S1? That is entropy change during this process. If we have changed the state of an ideal gas, pressure changed P2, P1 to P2, okay, then volume changed from V1 to V2, and temperature changed from T1 to T2. During this, what is the entropy change? That we want to calculate, and for that we are taking the help of first law of thermodynamics and definition of entropy, that is in ds is equal to integration dq by t. Here now we know the first law of thermodynamics here. So dq is equal to du plus dw, okay, but according to the definition of the cv, that is a specific heat at constant volume, we can say it as a du is equal to, we can define du is equal to cv dt. So here dv is equal to what, we can write it as a cv dt by the definition of specific heat at constant volume. So it is the heat required, it is internal energy. cv is a function of internal energy. It is the energy required or air to raise the temperature by 1 degree Celsius at constant volume. So that is the definition. Therefore, du is equal to cv dt. That is, you have learned the definition in first year, okay, or we can say cv is equal to du by dt, okay. So then we want to calculate this dq by t, okay, this dq by t we want to calculate, and for that we are considering it as a d q d here du is equal to mcv dt. So m is mass. For specific entropy, m will become 1. Okay. So dq is equal to mcv dt plus dw. We know the definition of dw. It is pdv work or pdv. But we want to get the value of dq by t. Therefore, we have divided this equation by t. Then we are getting equation dq by del q by t is equal to mcv dt divided by into dt by t plus pdv divided by t. Okay, but we know the ideal gas equation p by t is coming as what? mrt. So pv is equal to mrt. Therefore, p by t is coming as mr divided by v, and therefore ds is equal to mcv dt by t plus mr dv by v. Okay, then mcvdt epm m specific entropy, I'm always repeating, many times I'm repeating now. Specific entropy is there, m is equal to 1. Okay, then ds is equal to, in some books they have taken m is equal to 1, some books they are considering m is equal to m. Then we are calculating total entropy change. Okay, so ds is equal to mcv dt by t plus mr dv by v. Okay, that we have covered. Then we want to calculate now entropy change, the integration, integrating both sides. What we are getting? Integration s1 or 1 to 2 or s2 minus s1 is equal to what? S2 minus s1 we are getting here. Okay, so is equal to mcv. It is a split integration is there. So mcv integration t1 to t2 or 1 to 2 dt by t plus mr integration 1 to 2 dv by d or v1 to v2. And then we are getting finally formula, that is mcv ln of t2 upon t1 if you solve this integration plus mr ln of v2 by v1. So this is one formula. Everybody have to note down this formula in your notebook. S2 minus s1, that is at least derivation is also required. Many times they are asking the question that here derive an entropy change during and change of state of an ideal gas in terms of temperature and volume. The 4 mark derivation they can ask here in terms of temperature and volume. So this is our equation number 1. You can go for, okay, Roman 1, because we want now this entropy change in terms of temperature and pressure, maybe in terms of pressure and volume. Now we are getting temperature and volume, next maybe temperature and pressure, and afterwards it may be pressure and volume. Okay, now here, now this derivation we want in terms of now here temperature and pressure. And for that, what we are going to do is there, our ideal gas equation, we know that ideal gas equation p1 v1 upon p1 v1 upon t1 is equal to p2 v2 upon t2, and we want to replace this v2 by v1 by here this equation. V2 by v1 is equal to, we can say that here p1 by p2 into t2 by t1, or let it be now this is t2 by t1 we want to replace, and t2 by t1 is equal to v2 by v1 is equal to p1 by p2 into t2 by t1, and t2 by t1 is equal to p1 by p2 into t2 by p1 by p2 into v2 by v1. Okay, so both this is substitutions are there. This substitution we can take as appropriate place, and we can get the another equation for the change of state of an ideal gas. During that, how much entropy change occur. So substituting v2 by v1 in equation. Now this equation, let us this equation as 1 6 here I have taken from book screenshot. Therefore, this is in the 6.3.63 equation. Okay, this equation is there, or in our case it is a equation 1. Okay, so instead of that putting in equation 1. Okay, so what we are getting now here, s2 minus s1 is equal to mcv ln of t2 upon t1 plus mr into, instead of v2 upon v1 we can write p1 upon p2 into t2 upon t1. Okay, now in that case we can simplify it. mcv ln of t2 upon t1 plus mr ln of p1 upon p2 plus mr ln of t2 upon t1. Okay, so this t2 upon t1 ln t2 upon t1 we can take together, then it will become m into bracket cv plus r into ln of t2 upon t1. So combining, we are going to combine this t2 upon t1 terms, two terms. Okay, and mr ln of p1 upon p2. But we know that Cp minus Cv is equal to R. But therefore Cv plus R is equal to Cp. So we can write this as a Cp. Okay, so this is going to be Cp. Okay, therefore mCp ln of T2 upon T1 plus mR ln of P1 upon P2. Or if you want to write here in terms of like this, final temperature divided by initial temperature, this also, then this will become what? Here is equal to, here mCp as it is. Okay, mCp into ln of T2 upon T1, ln of T2 upon T1. So if we want to final pressure divided by initial, then minus mr ln of again P2 upon P1. So this is what another, this is another combination. Okay, so mCp ln of T2 upon T1 minus mr ln of P2 upon P1. So with the help of this equation, one can calculate again entropy. And this is another reform of the that the first equation, or we can give this equation as equation number Roman 2. So everybody write. I think I will give 1 minute time to you to write this derivation, this formula. Already I think written. Last lecture I think I have given time na to us, Kunal.
Yes, sir.
So already these steps are with you. This formulas are with you. Are these formulas are with you? Because we need to solve the numericals. To solve the numericals, we have to take help of this. Anybody can take? Or now write down. I will say share this PPT to you, but write down the formula at least so that we can solve the numericals. Somebody can reply whether you have written or I have to wait for some time. Suhas, Kunal, Ajit Gaikwad.
Two
Somebody can
minutes, sir.
reply. Huh?
Hello. 2 minutes.
Okay, wait. I will give time. So this formula, earlier formula also you can note down. This formula also you can note down because we have to solve the numericals on this. This is mr ln of P2 upon P1 minus, if you want to give minus sign. So this is the one derivation. Many times they are asking a question, that is derive an expression for entropy change during the change of state of an ideal gas in terms of temperature and pressure. Then earlier step we have to write directly, and then from this slide whatever is there we have to write here. This will have good weightage. Now next our step will be to get this formula in terms of now pressure and volume. Okay. Over na? Over? Suhas, Ajit, Kunal, over. Shubham, Shingan, over. Okay. Now similarly, what are the equation we got? The first equation mcv ln of t2 upon t1 plus mr ln of v2 upon v1 s minus 1. So here in this equation now t2 upon t1 value we have to put as it is. So what is t2 upon t1 value? So T2 upon T1 value will be here this P2 upon P1 into V2 upon V1. In that earlier equation, that equation number 1, S2 upon S1, if we put MCV ln of P2 upon P1, okay, into V2 upon V1 instead of T2 upon T1 plus MR ln of V2 upon V1. This we can write as a MCV ln of P2 upon P1. We can split, okay, plus MCV ln of V2 upon V1 plus already MR ln of V2 upon V1. Therefore, this will become MCV ln of P2 upon P1. Okay, so V2 upon V1 terms will take together. Okay, these two terms plus M into bracket CV plus R. We have taken this M into CV plus R as a common, okay, into ln of V2 upon V1. So this is a mathematical simplification. But we know that CV plus R is equal to again CP. This is a CP. This will become MCP ln of P2 upon 1. So this equation is now in terms of now MCV ln of P2 upon P1 plus MCP ln of V2 upon V1. So again with the help of this equation also one can calculate the entropy change during the change of state of an ideal gas. Here M is mass. If it is specific entropy, they asked us to calculate. M will become 0. Cv is specific heat at constant volume. Okay. P2 is the final pressure. P1 is the initial pressure. And volume is V2. Final volume is V2. Initial volume is V1. And again Cp is specific heat at constant pressure. With the help of this formula also, one can calculate the entropy change during this process. What is that? In terms of now, this is in terms of pressure, okay, and volume V. So again write down this formula. Okay. Now three formulas are there. According to that, we have to write some another equations. Okay. Now we want to write the equation for isothermal condition, isobaric condition, and isochoric condition. Okay. Now these equations are there. We will write the equation. Now, if the temperature is remaining same, isothermal process, if the ice here that change of state of an ideal gas occurs at constant temperature, then in that case here this T2 upon T1 will become what? Yeah, if isothermal condition is there, T2 upon T1 will become 1, and ln of what? Isothermal condition T2 upon T1 will become 1, and this ln of T1 is equal to 0. Therefore, isothermal condition S2 minus S1 is equal to Mr ln of P2 upon V1. So we can write here Mr isothermal condition. So for isothermal case, isothermal condition, isothermal process we can say, or isothermal condition here, what we can say here, T2 upon here, it will be delta S is equal to, or S2 minus S1 is equal to delta S is equal to, we can say it as a, what we can say, is equal to first equation. What is that? Mr ln of V2 upon V1. So Mr ln of V2 upon V1. With the help of this equation, if condition is isothermal, then if we know the two volumes, okay, and R value and mass of that gas, we can calculate the air delta S. Also, isothermal condition where temperature is there, then where is the temperature? Here also. If temperature is 0 here, then T2 upon T1 is equal to here T2 upon T1 is equal to 0. Then Mr ln of P1 upon P2 or minus Mr ln of P2 upon P1. So this equation we can also write as a or we can say minus Mr ln of P2 upon P1. P2 upon P1. So with the help of this equation also, one can calculate the entropy change minus Mr ln of P1 or P2 upon P1. Okay. Now let us assume second condition. This is one. So write down this isothermal condition. Everybody I request isothermal condition, isothermal process. Delta S is equal to Mr ln of P2 upon V1. Okay. Okay. Or minus Mr ln of P2 upon P1. Okay. Next is what? Let us consider isobaric condition. Write down this with me. Isobaric condition. Okay. If the pressure here isobaric case. So delta S is equal to what the delta S is coming for isobaric condition. Isobaric condition delta S is equal to now isobaric means what? P2 is equal to P1. Similarly, P1 upon P2 or P2 upon P1 will become 1 and ln of P2 upon P1 will become 0. Okay, it is constant. Therefore, isobaric condition, first equation, there is no pressure. Second equation, this will become 0. So mCp ln of T2 upon T1. So one formula for isobaric condition is that mCp ln of T2 upon T2 upon T1. This is one equation is there isobaric, or we can say isobaric condition. Now next another equation is there where pressure is coming as 0. So or mCp ln of V2 upon V1 or mCp or is equal to mCp ln of V2 upon V2 upon V1. V2 V2 upon V1. Okay, mCp ln of okay. This is isobaric condition. mCp ln of V2 upon V1 or mCp ln of T2 upon T1. Similarly, I want from your side now, I want isothermal process, isobaric process, and next is isochoric process. Entropy change. What is isochoric process? Entropy change. Isochoric process. So V1 is equal to V2. Isochoric process. Now I want from your side answers. What the delta S is coming as? Isochoric process delta S is coming as. Anybody? Delta S. Anybody? Anybody? Isochronic means what? V1 upon V2 is equal to, so isochronic 0. Why 0? So, not 0 na. This is what? Isochronic process V1 upon V2, that will be ln of V1 upon V2 will be 0, but some term will be there na. So it will be mcv ln of V2 upon V1 will become 0 here, but V2 upon V1 will become 0, but there is some term related to there, another term, that is mcv ln of P2 upon P1. So mcv, first equation we got it as a mcv ln of P2 upon, the volume is remaining constant but pressure is changing, or temperature also changing, or another equation is there, okay, is equal to m, what is the first equation is there, mcp, temperature we have got the equation na? It is mcv ln of T2 upon T1, or mcv ln of T2 upon T1. These equations are very important. Okay, so isothermal condition, this equation everybody's notebook, this formula should be there. Isothermal condition, delta S is equal to minus mr ln P2 upon P1, or mr ln V2 upon V1. Isobaric condition, mcp ln of T2 upon T1, or mcp ln of V2 upon V1. Isochoric condition, mcv ln of P2 upon P1, or mcv ln of T2 upon T1. So with the help of this equation, one can calculate the entropy change during the change of state of an ideal gas. And already many times I am telling here in this lecture, that is, these are the very important derivations are asking many times. That is, question is what? Write down question also. Derive an expression. Write down. Write down. Derive an expression. Derive an expression for change of state of an ideal gas. For change of state of an ideal gas in terms of pressure and temperature. Sometimes they will ask in terms of volume and temperature,
Sir,
and
repeat
maybe
again.
in terms of, shall I repeat?
Yes, sir.
Yes, sir.
Okay.
Repeat.
Derive an expression for, derive an expression for change of entropy, change of entropy, change of entropy during, change of entropy during change of state, change of state of an ideal gas, change of state of an ideal gas in terms of pressure and temperature. Now that combination can, this question will be remain same in terms of, now next they will ask pressure and volume. In term, last every earlier part is same, last part in terms of pressure and volume, and third may be there in terms of temperature and volume. So that way they can ask the questions. Okay. Now here, say whatever derivations we have gone for, same thing is here also. They have gone for in the PowerPoint presentation. What is entropy change during constant volume process? What is entropy change during constant pressure process? What is entropy change during constant temperature process? In the reversible adiabatic process, what is entropy change? Here it is going to be zero. Reversible adiabatic process means entropy change is going to be zero. Then how it is coming? So quickly we will go for. This is not our here. They are not asking in the examination, but formulas we have to remember. So irreversible adiabatic process, what is entropy change? Polytropic process, what is entropy change? We quickly will go for this now because already we have covered the derivation. Then heating a gas at constant volume process, let us assume. So let us consider m kg of gas. M kg of gas is what? Heated at a constant volume process. Let it is entropy is air, it is heated. Therefore, let us consider this as a S1. So 1 to 2. Let us consider this as the temperature T1 is the heated. So there they might consider this as T1. This is 1. This is what 2. Okay, and this will be T1. This will be T2. Okay, if it is heated, then what will happen? Then and dq is equal to what? Mcv, because it is heated at constant volume. Therefore, it is Mcv T2 minus T1 delta T. Mcv dt. Mcv dt means T2 minus T1. Okay. Small change in heat supplied. dq is equal to Mcv dt. Dividing both sides by T because we want dq by T. Okay. And therefore, Mcv dt by T. Therefore, it is equal to Mcv dt by T. Already we got that equation. If we integrate this, we are getting this equation mcv ln of t2 by t1. So already in our equation we have gone for which condition? Volume isochoric condition, mcv ln of t2 upon t1. This equation is there. So last equation is there. Okay, this equation is there, mcv ln of t2 upon t1. So in that case they have achieved this equation in this derivation. So now we'll go quickly through this. Okay, so this is one equation is there. Already we have written. Everybody written that equations. Huh? Then heating a gas at constant volume, pressure. So if the pressure is constant, then definitely this equation will be mcp instead of cv. It will only change will be there, that is mcp, because instead of volume, constant volume, here we are heating the gas at constant pressure, and it is equal to mcp ln of t2 upon t1. So already this we have covered. Then isothermal process or constant temperature process. T1 is equal to T2. Okay. Then gas is heated. Then how much entropy change is there? So TS diagram is there. There we have shown here. This is a plot TS diagram. Let us consider the gas is heated from temperature one state 1 is state 1 to state 2, and during this state temperature remaining T is equal to constant. This is entropy Ts1 is entropy S2. What is this entropy change? S2 minus S1. This delta S they are asking. This is S2 minus S1. This is the delta S they are asking. What is this here? And for this we know the equation. So dq is equal to same. dq is equal to du plus dw. Same thing we are going to repeat. dq upon t p by t dv. Okay, as they know that here delta in that here isothermal condition, therefore internal energy will not change because internal energy is a function of temperature. If temperature is remaining same, du is equal to 0. Therefore dq is equal to only p by t. Okay, therefore ds is equal to mr dv by v, and equation is there, mr ln of v2 upon v1. Or whatever derivations we have solved, from that we can apply the condition, that is T2 upon T1 is coming as what? Ln of T2 upon T1. That what the derivation is there? Ln of T2 upon T1 is coming as 0. Ln is coming as 0, not entropy change. Therefore, remaining part will be the entropy change for the change of state of an ideal gas at constant temperature condition or isothermal condition. Okay, now reversible adiabatic process is there. Okay, so this is reversible adiabatic process, means entropy change for this reversible adiabatic means 1 to 2 is a reversible adiabatic. Okay, it is called isentropic. And as adiabatic process, we know that dq delta q, there is no heat we are supplying to the adiabatic process, or we cannot, the system cannot get reject also the heat. Therefore dq by t for adiabatic process is equal to what? dq is coming as what? For adiabatic process, write down, for adiabatic process dq is equal to 0. Adiabatic process what? dq is equal to 0. Therefore ds is equal to dq by t is equal to 0. Therefore it is equal to delta S coming as what? 0. Therefore, write down for reversible adiabatic process on TH diagram, entropy is remaining constant. There is no change in entropy, means S1 is equal to S2 as S. No change in entropy, therefore S1 is equal to S2. Okay, write down for reversible adiabatic process, entropy change is equal to dq is equal to 0, and therefore delta S is equal to dq by t is also equal to 0. Therefore entropy change is not there. Therefore entropy remains constant. Therefore entropy is remaining constant. Okay, then therefore, reversible adiabatic processes are called as isentropic processes. Write down this. Everybody writing. So for adiabatic process, this we will write down because this is asking many times. Okay, this is knowledge. These are adiabatic process. Write down. Adiabatic process dq is equal to 0. Therefore, change of entropy is equal to ds is equal to in del q by t is equal to 0. Okay, and therefore S1 is equal to S2, and therefore write down reversible adiabatic processes are called as isentropic processes. Isentropic processes. Because why isentropic? Because meaning of isentropic, anybody? Isen means anybody? English. Isenthalpic, isentropic. Anybody? And isentropic means what? Entropy remaining constant or constant. Okay, reversible adiabatic process, isentropic process, entropy is remaining constant. Therefore, these are called as reversible adiabatic processes are called as isentropic processes, and during them entropy change is equal to 0. Now, irreversible adiabatic processes. Whatever the adiabatic processes are there, so these are adiabatic process, reversible adiabatic. Here, if reversible adiabatic processes are del q is equal to 0, then it is always greater than if adiabatic process with internal friction, it is known as irreversible processes, or any all the processes in the universe are irreversible processes. Then if the irreversible adiabatic expansion process takes place between same temperature limits T1 and T2, and due to internal friction, the internal energy of the gas at the end of expansion will be more than at the point 2. Therefore, suppose del Q is the heat gained by the gas due to internal friction, then the increase of entropy will be given by S2 minus S1 is equal to del Q by T, or generally we say that here always result in increase of entropy. So therefore, for reversible adiabatic processes, irreversible adiabatic processes, delta S or ds is always greater than 0. ds is always greater than 0. For which processes? Irreversible adiabatic process. Write down. For irreversible adiabatic processes, or all the processes in the universe are irreversible. So for all these processes, entropy change is equal to greater than 0. 0 means adiabatic process or reversible processes, and greater than 0 means it is irreversible processes. It means that higher entropy at the end of expansion for irreversible process. Therefore, work done by gas will be less than that of reversible processes. And if you want to supply, then for irreversible process, we have to supply more amount of work. Okay. So S2 minus S1 is always greater than 0. Then they have given one process, that is polytropic process, entropy change during polytropic process. Okay. So here consider m kg gas expanded polytropically from 1 to 2. It is following the law. It is 1 to 2. It is follow. Okay. So this is going to be 1 to 2 process is there polytropic. It will follow the law. PV raised to n is equal to PV raised to n. PV raised to n is equal to PV raised to n is equal to constant or C. Okay, it is following the law. Then entropy TS diagram, entropy related to point 1 will be S1. Okay. The entropy point related to this will be S2. As temperature decreasing, okay, this is a expansion process, we can say expanded gas is expanded. If it is a compressed, one will be here and two will be here. Then again equation, dq is equal to du plus dw. Okay. Then here dq is equal to mcv dt because the internet function pdv. Okay. Therefore this equation now, dq by t, this is not an our derivation but we change, let it be, dq by t is equal to mcv dt by t plus p by t dv. So if we put this condition, same equation, mcv dt by t plus mr, because p by t will be equal to pv is equal to mrt. Therefore pv is equal to mrt. Therefore p by t is equal to mr divided by v. Okay, that we have gone for the derivation. And ds is equal to mcv dt by ln t1 to t2 integration dt by t plus mr v1 to v2 dv by v. Or we can say s2 minus s1 is equal to whatever derivation we got, s2 mcv ln of t2 upon t1 plus mr ln of v2 upon v1. Okay. Similarly, in terms of pressure and volume, whatever we have done for same thing we have to do. Okay. And in terms of pressure, temperature, they have got. Similarly, all these cases are going to be same. Okay. Now here this is very important. Entropy change. Okay. Up till now, everybody has written the formulae. What I have told in the first slides. All of you have written, because these formulas, without these formulas, derivation we can go for it, but without formulae we cannot solve the numerical. Up till now, all have written the formulae, change of entropy, entropy change during change of state of an ideal gas. Okay, Kunal is giving answer, Shubham is giving yes, others, Kunal Shetty, okay, Shubham Singhan, others, reply because okay. Or you can if you want, don't having laziness to write, at least unmute your phone, unmute yourself. Okay, and tell yes sir or not. Now because we are going to now important part. Okay, shall we go ahead? Shall we go ahead? Okay. Yes. Okay. Now entropy change of a pure substance. Oh, this is very important. Huh? Now consider m kg of ice. Okay, let us say it is having temperature less than 0 degree Celsius. Okay, and heated continuously at constant atmospheric pressure. Okay, it is heated here, some difference here. It is heated continuously at atmospheric pressure. Okay, this is ice is there. We have taken 1 kg of ice or m kg of ice we can take. Okay, then if it is heated with the help of heat, one symbol. Okay, with the help of heat, if this ice is heated at constant pressure, means atmospheric condition, then what will happen? Okay, now first of all I want to from your side that somebody can unmute and you can tell, if imagine that ice is there, don't worry about mass, ice is there in the atmospheric condition and we have started heating that ice, what will happen to that ice? That because and on this our entire subject now depends, our knowledge of entire subject understanding depends on this diagram. Anybody can reply and tell? Don't write now because reply and tell, unmute and tell. What will happen? Your imagination, what will happen? What you have learned up till now, who will tell? I'll be happy with that person if he is telling correctly. Anybody is unmuting and telling? Let us.
Volume decreases.
What happened? Kunal.
Volume decreases.
Volume decreases. Okay. Then another thing. After some time, volume may also increase, na? Process, you tell process. What will happen? Volume decrease. Okay. Then, okay. Now let us understand.
Sir,
Uh, uh,
uh, entropy increases.
because we are supplying the heat, entropy will increase. Good. One answer. Volume decrease. Another answer. Okay. Then anybody other than you two, Kunal and Ganesh, Gaurav, na? Gaurav Karande. Hmm. Any other than them? Ice is melting. Who is giving? Shingan. Correct. So basically, what will happen first? Ice will start melting. It is there, melting of ice. Okay, but now what will happen? Now I will tell. Here, everybody have to concentrate. And afterwards, we'll write the diagram. But this is about our change of state or change of phase. Now, here concentrate. There are three, what you can call, there are three stages, okay, or states. We can call it as states of a substance. One is solid, another is liquid, and next one is vapor or gas. Now remember that this is our temperature. Now coming to this particular diagram on slide, what is there? This is the temperature axis. Y is on where we plot the temperatures, and here entropy is there or enthalpy. Here we can say it entropy or enthalpy heat. Where heat is added means entropy goes on increasing. Similarly, enthalpy, specific enthalpy is also goes on increasing. Now what will happen to the ice? Now let us consider the initial temperature of ice is equal to T1. Initial temperature of ice is equal to T1. And it is less than 0 degree Celsius. And whatever this line is there, this is the nature of constant pressure line. So here along this line, 1, 2, 3, 4, 5, 6 states are there. Along this entire line, the pressure is remaining constant. So pressure is remaining constant. And this pressure is called as what? Atmospheric pressure. Along this line, pressure P is equal to, I'll write in short, pressure P is equal to constant along this line. Okay. Now what will happen? First of all, the ice at 0 degree, negative degree Celsius, we can consider minus 10. Let us consider the magnitude, minus 10 degree Celsius. And this ice, when it is put in atmosphere, and if we give heat, what will happen? First of all, it starts changing its stage, means from solid to liquid. But this will not happen suddenly. What will happen? First of all, the ice will be heated and its temperature will start increasing from temperature T1 to temperature T2. And this way, entropy goes on increasing. We are adding this particular heat. So first of all, temperature is increasing from T1 to T2. Now T2 is considered as what? 0 degree Celsius. Now when this 0 degree Celsius will reach, what will happen? What will happen? I want interaction for this because this is the entire subject depends on this diagram. Steam table depends on this diagram. Now what will happen? When 0 degree Celsius temperature will reach, from minus 10 degree Celsius to 0 degree Celsius, heating is goes on, temperature will increasing. Okay, but when 0 degree Celsius will reach, what will happen? Afterwards, what will happen? Temperature remaining, isothermal case, temperature remaining constant. Okay, now first of all, that ice will take the heat, and that heat is called as sensible heat. It is called as what? Sensible heat. So write in your notebook what is meant by sensible heat, or who will tell definition of sensible heat. There are two heats we are going to take into consideration. One is sensible heat and another is latent heat. Okay, now who will tell definition of sensible heat now? According to this, sensible heat, anybody? If it is problem to Write and unmute and tell. What is the definition of sensible heat? Not knowing. You write down in notebook. Write down. The heat, the amount, the part of total heat. Write down. The part of total heat, the part of total heat, which is responsible, which is responsible to increase the temperature of a substance. To increase the temperature of a substance. So that kind of heat is there. It is called what? Sensible heat. Anything is there, its temperature is increasing. If you heat that thing, that is called as sensible heat. Agree with me? Sensible heat means what? The heat component of heat or part of total heat which is responsible to increase the temperature. Now from minus 10 to 0, it will increase the temperature. But when 0 degree Celsius will reach, this will be that ice will be in solid state. It will be saturated now. It will be saturated, and at this 0 degree Celsius, okay, will reach, that is point number 2, state 2, where considering as state 2. What will happen here? If we supply the heat at state 2, now the temperature of ice at 0 degree Celsius will not remain constant. Sorry, will not increase. Temperature of ice will not increase, but it will remain constant. And then whatever the heat we are giving to that ice at 0 degree Celsius, where it is utilized, where it is used, anybody? Anybody can unmute and tell where that heat is going? Where it is going? Temperature is remaining constant, but what is that with that? What is that heat? Whatever we are giving? Anybody? Nobody is replying. What you learned in basic mechanical? Okay, so I will tell. Okay, so here what will happen? This heat is utilized to change the phase, of that particular substance. Now here it is at point number 2. What is that point number 2? It is the ice at 0 degree Celsius. We can get it as a ice at 0 degree Celsius. And here we are getting what? We are getting it as a ice, not ice now. From point number 2 to point number 3, phase conversion occurs. This is called what? Phase conversion. It is called what? Phase conversion. This phase is changing. Or we can call phase conversion, or we can say it as a phase change. It is what? Phase change. Now during phase change, what is called? It is a phase change. This is ice is converting into water. Ice is converting into water. So 0 degree Celsius ice is get converted first upon 0 degree Celsius water, and this is called as phase change process. Ice is 0 degree Celsius ice is converted into 0 degree Celsius water, and what will happen here during phase change? So first of all, what's about temperature? We'll tell about temperature during any phase change. It may be solid to liquid, liquid to vapor. Any phase change, the temperature of the substance always remain. Anybody? Any constant. Temperature always remain constant. Write down now. Phase change. Write down in your notebook. During any phase change, temperature of substance remains constant. Temperature of substance remain constant. So this is a basic idea. Any phase change, you can go anywhere. This is our basic. There during here phase change, temperature remain constant. So T2 is remaining constant, and this heat is called as, whatever the heat we are supplying from point number 2 to point number 3, it is phase change from ice to water, where temperature remaining constant. So that heat is called as, anybody? That is heat is called as, anybody? That heat is called as, nobody is replying. Unmute and tell. Let it be wrong answer. Why? Whether I am punishing. I am here in college. You are here at your home. How in? Okay. How I can come to you? Gorak. Gorak Konduvari. It is called as
Latent heat.
latent heat. Correct. It is called as latent heat. Shubham, it is not phase change heat. It is process is phase change, but heat is called as latent heat. Write down now in your definition notebook. Latent heat. Latent heat. Write down. Latent heat. Are you writing now? Latent heat. Write down. Amount of heat. Amount of heat. Amount of heat which is utilized. Amount of heat which is utilized for phase change of a substance by for phase change of a substance in bracket maintaining temperature constant, maintaining temperature constant, maintaining temperature constant. So during any phase change, what will happen? During any phase change, what will happen? Temperature always remain constant, and this is called as latent heat. Okay, or it is called as now HFS, latent heat of fusion. It is called as fusion means ice is melting, therefore it is called as what? HFS. And notation is what? HFS. Anybody, everybody got latent heat of fusion? Temperature remaining constant. Okay. Now, shall we proceed? Okay. Now at point 3, at phase 3, what is our condition is there now at 3? At 3 is what? At 3, point number 3 is what? Temperature is 0 degree Celsius. What is the phase? Now what? It is not in ice condition. After melting, ice will be converted into, anybody? Ice will be converted into liquid means, correct, water. Okay. Why ice is converting into what? Liquid means it is going to be water, or any substance we can say it as a water. So at point 3, it is here we can say 0 degree Celsius water is there. Okay, correct. Then this water at 0 degree Celsius. Now still we are heating that water at 0 degree Celsius. What will happen? Its temperature now, what will happen? Directly phase will not change. Its temperature will start increasing from T2 to T4. Let us consider this as a T4. Let us, this temperature will increase from T3 to T4. This temperature will increase from T3 to T4. Okay, and this heat, as temperature is there increasing, and which heat is responsible? It is sensible heat. So this is called as what? S3 minus S4, or it is if it is a heat, it is going to be which heat is there? Sensible heat, or the heating is called as sensible heat, because in this case the heat temperature is goes on increasing, and as temperature is goes on increasing, so this part of heat is called as what? Sensible amount of heat, sensible heat. Okay. Now here again point number 4. What is there? Saturation temperature will reach, and this is equal to, anybody, at atmospheric condition, what is saturation temperature of water? Means at what temperature water is converted into vapor? Anybody can reply? Right, I am writing. Anybody? Let it be wrong. Why? What is saturation temperature? काय आपले सगळे मित्र आहेत की हो, काय लाजताय घाबरताय? येस येस येस, आय एम गेटिंग आन्सर. सुजित माने, शुभम गांडुळे. ओके, answer is what? 100 degree Celsius. Let it be. Okay, good. So this is going to be 100 degree Celsius. So what will happen here? From point number 3 to point number 4, temperature will increase from 0 degree Celsius to 100 degree Celsius, and that heat is called as sensible amount of heat. But at point number 4, when the saturation temperature, it is called what? TS, saturation temperature, because afterwards the temperature in the water form, temperature will not increase. Then temperature is get saturated. Therefore, it is called as saturation temperature. At point number 4, the saturation temperature will reach. And if we add the heat at this juncture, if you add the heat at this juncture, then whatever the heat we are utilizing is used, or it is we are giving, whatever heat we are giving is used for anybody, used for change of phase from water to vapor. It is called what? Vapor, or we can say it as a vapor, or we can say it as a steam. It is called what? Steam. It is called what? Steam. Vapor or steam. Okay. So this heat means what? Amount of this heat is there. This is again called as which amount of it is sensible heat or latent heat? Anybody? It is sensible heat or latent heat? It is latent. Sujit Manik giving correct answer. It is what? Sensible latent heat. It is what? Latent heat of vaporization. Therefore, it is called as HFG. Okay. Here HFS means what? Latent heat of fusion. It is latent heat of vaporization. So temperature always remain constant. Again, temperature T is equal to constant. So T is equal to constant, and HFG is there. And then afterwards, when steam is converted, okay, into complete form, okay, it is called as, at this point, it is called as saturated steam. It is called as what? Saturated steam, because it is having temperature equal to saturation temperature. Hence, this steam is called what? Saturated steam. Now, from point number 5, if you are increasing its temperature, if still we are heating that steam, till we are hitting that steam, what will happen? Now this is very interesting. What will happen? Somebody have to reply now. What will happen? If at point number 5, if we will heat that steam, its temperature will
increasing.
Kunal,
Increases.
temperature will increase, correct na? Temperature will increase, and this steam 5 to 6, it is called as superheating of steam. So sensibility is superheat, is one of the name we are giving it as a superheat. Okay, superheat is mass temperature which goes on increasing, and it is goes on more than saturation temperature. So this is called as superheating of steam, and that steam is called as superheated steam. The steam is called as what? Superheated of steam. Okay. Now, in our syllabus now, we are having entropy change during phase change process. Entropy change during phase change process. Write down in derivation now. Okay, 1 minute. I'll take one slide for our writing. Okay. Now write down entropy change during phase change process. Entropy change during phase change process. Write down heading. Entropy change. You heading with me. Write down with me everything. Entropy change during phase change. During phase change. This is our last article of this. during phase change. Okay. Write down first. Here, first phase is what? Phase change from solid to liquid. First, write down solid to solid to liquid. Now, write down what is entropy change formula? We know ds is equal to integration or 1 to 2 dq by t. dq by t. Okay, this equation write down. Now, what's about temperature during phase change? Now I am writing entropy change for during phase change. So phase change process. What is temperature? Whether temperature is changing, remaining constant, or increasing, decreasing. Somebody can tell fast. What happens during this entropy here?
Remains constant.
Phase change process. Temperature always remain
Constant.
constant. Therefore, this T I can take it as a outside this bracket because temperature remaining constant. And integration of this dq, this is what? Total amount of heat taken from integration means total amount of heat taken during phase change process. And now we are considering it as a solid to liquid. Therefore, that heat is called as anybody. We can go to this diagram. So it is called as this difference of amount of heat, total amount of heat taken during the phase change from solid to liquid. What will be the equation? Anybody? What is the amount that is equal to HFS divided by T. Okay, write down now. This is a very important equation. Okay, what is that? Solid delta S is equal to integration dq by t 1 to 2 is equal to 1 by t. And why 1 by t? We have taken t constant because t is equal during phase change, temperature remain constant. That we write down. Temperature remain constant. Therefore, 1 by t integration dq, and integration dq is equal to total amount of heat that substance has taken during the phase change, and is equal to HFS divided by T. So ds is equal to HFS divided by T. Write down where HFS is called as anybody. काय म्हणतो आपण HFS ला? What we call it HFS? What we can call HFS? Anybody? It is called as which heat? Sensible or latent?
Since
Huh? HFS is what? Anybody? Which heat?
Latent
It
heat.
is as phase change. Which it is responsible? Latent heat.
Latent heat.
Latent heat of okay, latent write down where HFS is equal to latent heat of fusion. Because fusion means ice is converting into liquid. Latent heat of fusion. Write down. So entropy change during phase change process is given by equation ds is equal to integration 1 to 2 dq by t. T is remaining constant. Therefore, we are taken outside integration dq. So during this process, entropy during phase change process, how much amount of it will be there? HFS divided by T. T is there. The integration of dq is HFS, and where HFS is only latent heat of fusion. You got this? Similarly, what we have to go for? Another phase change that we have covered in our diagram. What is it? Another phase change. Which phase change we have covered? Liquid to इथं liquid आहे आणि इथं काय आहे? Vapor. Liquid to vapor. So another phase change is there. It is what? Anybody? It is going to be liquid to vapor. Again, same diagram, same thing we have to repeat. Liquid to vapor. Liquid to vapor. Again, Write down everything. I am writing. ds is equal to, again formula. What is ds is equal to? Integration 1 to 2, because this is our dq by t. So understand my handwriting. I am taking, means I am with mouse I am using pen. Okay, take that. Okay, dq by t and is equal to, again it is which pressure process phase change. Therefore again temperature remaining constant, 1 by t integration dq. But what is this dq is called as? Anybody? It is called as what? 4 to 5, liquid is changing to vapor, and that heat is also latent heat of, anybody, evaporation or vaporization, and it is denoted by letter hfg. What is that? Here it is going to be t is constant, and this total entire amount of heat is we are denoting by hfg. Okay, divided by t. Okay, so ds is equal to hfg divided by t. Okay, now here hfg is called as, anybody, already discussed. hfg is called as, again it is not sensibility, which heat? Latent heat. Latent heat of vaporization or evaporation, we can say latent heat of vaporization or evaporation. Sometimes in some books they have written as a evaporation. Okay, latent heat of evaporation or latent heat of evaporation. So these two derivations are very important. Entropy change for during phase change process, or entropy change during change of state of an ideal gas. I'll repeat now. Solid to liquid, if the phase is changing, ds is equal to hfs divided by t, and where t is the temperature at which the solid to liquid phase conversion occurs, temperature at which it is in Kelvin. Okay, HFS, and where HFS is called as latent heat of fusion. Another phase change that we can come across is liquid is changing to vapor, liquid to vapor. Again, ds is equal to integration dq by t, integration 1 to 2 dq by t is equal to 1 by t, because t is remaining constant, integration dq, and is equal to hfg divided by t, and hfg is called as latent heat of vaporization. Okay, now with this we'll solve our, so this is we'll cover afterwards, but now I want the answer from your side. So these numericals are asked for 2 times in the university examination. What is that numerical? Ice melts at 0 degrees Celsius. Ice melts at 0 degrees Celsius with latent heat of fusion is equal to 339.92 kilojoule per kg. Okay, kilojoule per kg means m is equal to 1, they have given. Water boils at atmospheric pressure at 100 degrees Celsius with hfg is equal to 2257 kilojoule per kg. Okay, and find now, what is that? Find entropy change. Find the entropy change. I can find entropy change. There are 2 cases where to supply. Find entropy change. During above processes. above during above processes. Now find the entropy change during above processes. Now calculate. Shall I give time to you? Already I have given the formulas to you. Only thing is there that we have to convert these temperatures into anybody. This and this temperature. Two cases will be there. So first is entropy change during ice melting. We can consider. Okay. First case, and another is entropy change during water evaporation or water boiling. So temperature we have to consider it into Kelvin. That care we have to take. So first answer we got Kunal Shetty 1.245, Shubham Gandoli 1.245 and 6.05. Correct. The answer unit should give. What is the unit for the entropy change? Or entropy change, entropy unit kilojoule, as it is per kg kilojoule per
kg Kelvin.
kg Kelvin. Okay, entropy change kilojoule per kg Kelvin. Every here value we have to write the unit. Shall I go for calculation directly? Correct. So it is what? Here entropy change. So SSF means entropy change. Okay, is equal to what is the formula? Delta S we know that it is equal to HFS divided by T. Okay, HFS value they have given 334. This will be 334.92 they have given. Temperature is in Kelvin. 0 degree Celsius means Kelvin 273.15 Kelvin. Okay, and in that case, as it is mass is equal to 1, therefore kilojoule per kg Kelvin. Per kg, per mass. If it is mass, it will be more than 1 kg, then it will be, your answer is correct, Shubham. Kilojoule per kg Kelvin. So it is a 1.226, okay, kilojoule per kg. So I think 3 4 and SFG. Now next delta S for, this is case 1. We can say it as a case 1. First case is there, and second case is what? SFG means it is ds is equal to, again here formula, HFG divided by T. HFG divided by T. Answer is what? 2257 divided by 373.15 and is equal to 6.0485 kilojoule per kg Kelvin. Okay. So this way, when 4 marks they are going to ask, so ds is equal to HFS divided by T. So I request everybody to write down the formula in your notebook, derivation formula. You have to request during lecture that sir, stop sir, we are writing. That way I can understand. Shall I proceed? This everything you have written on from the screen. From the screen, everybody have written. So other than Kunal and Shubham, Suhas Naste is present in class. Okay.
Yes, sir, written.
Okay. So next numerical. So ice melts at. This numerical already we have taken, correct na? Calculate entropy change Okay. Calculate entropy change if 1 kg of water at 30 degrees Celsius is heated to 80 degrees Celsius at 1 bar pressure. The specific heat of water is 4.2 kilojoule per kg Kelvin. Okay, now without this formula, okay, so because we are having less time, if I will take this numerical partly. So write down, calculate entropy change if 1 kg of water at 30 degrees Celsius is heated to 80 degrees Celsius at 1 bar pressure. The specific heat of water means at constant pressure. So as they have given it as a 4.2 means it is specific heat at constant pressure. So pressure is remaining constant. Now at constant pressure we have to calculate the entropy change. What are the formulas are there? At constant pressure, what are the formulae? Delta S is equal to, write down, at constant pressure entropy change is given by, entropy change is given by, entropy change is given by, correct na? This formula is correct. We have derived na this formula.
Yes,
Have
sir.
you derived this formula? At constant temperature, at constant pressure. Okay. So what is formula? If we know the board temperature, T1 is this is T1. This is what? T2. Oh, sorry. T1 is 30 degrees Celsius and T2 is 80 degrees Celsius. So T1. Given data, you can convert that. T1 is equal to, what is T1 is equal to? Here 30 plus 273. Okay. And T2 is equal to 80 plus 273. Okay. Delta is equal to Cp ln of T2 upon T1. These numericals are asking for 4 marks, but for that we should know the correct formula for that numerical. Delta S is equal to Cp ln of T2 upon T1. Okay, and this is equal to what? 4.2 kilojoule. You can directly calculate in kilojoule, no problem. So 4.2 kilojoule per kg Kelvin they have given into T2 upon T1. So it is equal 273 plus 80 divided by 273 plus 30. So you can get answer as a minus 0.6415 kilojoule per kg Kelvin. Written. This is such kind of numerical they are asking for 4 marks. Only we should at that time we should struck the correct formula and what is given and what is asked. What is given data we have to write. Unit conversion also we have to take care. Now here I will give the numerical. Write down. Calculate. Over now numerical over. My students are not interacting. Yes sir. Hello sir. That is requirement for me. I am here. You are 200 over. Okay. Shubham Gandu. Only few are few. Shubham is only responding. Others, at least in message box, at least unmute. तेवढं बरं वाटतं जरा मी एकटाच बोलतोय तुम्ही जरा बोललेलं बरं वाटतंय unmute and tell Kunal City. Okay, yes sir. Now next numerical, write down. I am now giving numerical on dictation only. Calculate entropy change. Calculate entropy change for 2 kg of water. For 2 kg of water. For 2 kg of water at 60 degrees Celsius. At 60 degrees Celsius. So I am giving m is equal to 2 kg. 60 degrees Celsius to 90 degrees Celsius, to 90 degrees Celsius, add 1 bar. The specific heat of water is 4.2. Same. The specific heat of water is 4.2 kilojoule per kg Kelvin. In 2 minutes I want answer. Water mass is not now 1, it is m. Therefore, formula will be m is equal to, it is equal to m into Cp, m into Cp ln of T2 divided by T1, because here mass is given. The answer I want fast. 0.72 kilojoule per kg Kelvin. Here Kunal, kg is not required because mass we are multiplying. Therefore, answer will be 0.72.
Hello.
Am I audible? Okay, this is last numerical we'll take, and we'll wind up our lecture. Nobody informed me that I am outside. Huh? Okay. So write down numerical. Calculate the entropy change for 1 mole of an ideal gas. Calculate entropy change for 1 mole of an ideal gas expanding isothermally from a volume of 24.4 liter to 48.8 liter. Okay. So what is the equation is there? Isothermally. So gas is what? Expanding isothermally they are given. So gas is what? Expanding isothermally. Therefore, isothermal formula is what? Delta S is equal to anybody? Delta S is equal to
MR.
MR, huh?
LN.
MR ln of
LN.
V2
V2
upon
upon
V1.
V1.
But as it is M is there, we can say it as a M is we can replace by NRT. Okay, it is equal to NRT also. So here is equal to be NR, mole is there, but R we have to take it as a 8.314. So remember that here I am giving you one hint, that is R constant for air is equal to, remember that R is equal to anybody 8.314. It is with respect to kilojoule per mole per Kelvin. Remember that. This is R constant is what? 8.314 kilojoule per mole per Kelvin. And R is equal to anybody in terms of kg? 287 kilojoule per kg Kelvin, or we can say here, sorry, 287 joule, 287 joule joule, or we can say 280.287 kilojoule per kg Kelvin. This everybody notebook you have to cover. So in terms of mole, it is equal to here 8.314 kilojoule per mole Kelvin. Okay. Sorry, joule, sorry, it is going to be not kilojoule, it is also joule. Remember, here you can go for, here it is going to be kilojoule. 8.314 joule per mole Kelvin, and here 287 joule per kg Kelvin. So instead of that m, we can consider it as a n. Okay, and their answer will be delta S is equal to NRL V2 upon V1. Then ratio both units should be same. Okay, therefore 100 mole. Okay, is there 1 mole R will be 8.314 joule per mole Kelvin, and ln is equal to 40. So ln of 2, this will become 2. Okay, so is equal to what? Finally here, if you write this here, 1 into 8.314, okay, into ln of 2. It is going to be 5.760 joule per Kelvin. Okay. Now, homework numerical. Calculate entropy change for 1 kg of ideal gas. Calculate entropy change for 1 kg of ideal gas. Changing its volume from 5 meter cube to 15 meter cube. Calculate entropy change for 1 kg of ideal gas. Changing its volume from 5 meter cube to 15 meter cube isothermally. Okay, shall we stop here? Anybody? At least everybody replied, yeah, yes, no.
Yes, sir.
Yes, sir. Yeah, who is giving? Good. So, Soham Orikar, only this, you have spoken only 1 minute, 10 seconds for this. Okay. So, we'll stop here. I think everybody might have taken numerical. And next lecture, we'll start our second chapter. And very important that steam tables I am going to cover. So, don't miss the lecture. Okay. Now, you give remaining students give your attendance by roll number, and you can quit the class.